Hey AP, in this video we're going to talk about Lewis structures and hybridization. So Lewis structures is a topic that we have covered in chemistry, so that part's going to be mostly review, a couple new terms there. And then hybridization is a new AP thing that we haven't talked about before. When I was in your shoes, hybridization was confusing. So I'm going to do my best to make it as unconfusing as possible. We're going to learn about the background behind it. And then after that, we'll look at, what's the shortcut then. So similar to what you do in math, you learn how to do something by hand. And then we say, hey, your calculator can do it. We're going to do that with hybridization today as well. So, and then this video is a little long, but I'll pause and have spots for you to copy some stuff down because there's a little bit of writing to do towards the end. So Lewis structures, like I said, is something we've talked about before. And Lewis structures occur between covalently bonded atoms. You'd never draw a Lewis structure for an ionic compound or a metallic compound. And that's because Lewis structures show the sharing of electrons. Remember, the octet rule is that every atom wants to have 8 electrons, except hydrogen wants 2, helium wants 4, and boron wants 6. Those are our exceptions. When we draw Lewis structures, we start by counting valence electrons up for each atom. I should grab my periodic table. So on our periodic tables, remember that the group that they're in determines their number of valence electrons. Well, that's one of the ways it was organized. So we can look to see their group number by ignoring the transition metals, can get their number of valence electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. Then we're going to put the least electronegative atom in the center, except for hydrogen. Hydrogen only wants one bond, so we can't ever put that in the center. It just won't bond with more than one thing. Then we'll go and fill everybody's octets. We'll count up the total number of electrons and see if they match the total number of valence electrons that we're actually allowed. If there's too many, we'll take a pair, and make them share. And if there's too few, which is new, we'll add pairs of electrons to the central atom. So let's go ahead and draw Lewis structures for diatomic nitrogen and then PCl6 minus 1. So first we need to count valence electrons. I have nitrogen and I have 2 of them, 2 nitrogens. Each nitrogen has 1, 2, 3, 4, 5 valence electrons. So 2 times 5, there's nothing else here. So it gives me 10 electrons to play with. I put my least electronegative atom in the center. There's only 2, so there's no center. So I'm going to put my nitrogen to my other nitrogen, and I start with just putting that single bond between them. And then I'm going to go ahead and fill everybody's octets. So remember, this bond counts for 2 valence or 2 electrons that are kind of being shared back and forth, and they want to have a total of 8. So I add 2, 4, 6. Plus these 2 shared makes 8. Same thing for their side. I've got 2 here, 4, 6, and 8. So everybody has their octets filled. I'm going to count up my total number of electrons. 2, 4, 6, 8, 10, 12, 14. Well, I really only have 10 to play with, so I've misrepresented my Lewis structure. So if I have too many, I'm going to take a pair, and make them share. So there's really not 4 there. There's actually just 2 being shared between them. So I'll redraw. If you had pencil, you just erase and redraw it. So now, instead of having these 2 lone pairs, I'm going to add a second bond. So I'm at a double bond. So I count again. 2, 4, 6, 8, 10, 12. That's still too many. So again, take a pair, make them share. And they have to take from each side equally because they like to be symmetrical. So again, this is what I had. I took a pair, made them share, and now I've got a triple bond. Nitrogen's pretty famous for having triple bonds. It just likes them because of its 5 valence electrons. So 2, 4, 6, 8, 10 electrons. That's how many I actually have to use. So it's a happy structure. That's what it's supposed to look like. Okay. Let's take a look at PCl6. Well, notice this time we have more than 4 things connected to our central atom. called an expanded octet. So again, that's something that's new here in AP. So we've got phosphorus and chlorine, 1 phosphorus, 6 chlorines, and then I've got this -1 charge. That means that we're adding an electron to have us have paired electrons and everybody be satisfied. So phosphorus is underneath nitrogen, so 5. Chlorine over here has 7. So times 5 times 7, 5, 42 and 1, 43 and 5 makes 48 electrons. It's quite a bit. My most electronegative element goes in the middle. Okay, so that might make you think that chlorine goes in the middle, but that would make for an asymmetric molecule, and molecules don't like to be asymmetric if they can help it. So in this case, phosphorus is going to go in the middle. Chlorines are going to go around it. Now, usually with the way that we write molecules and formulas, that first atom that's listed is going to be the central atom. So that's another way you can tell. So I'm going to put my phosphorus in the middle. We want to evenly space this out. So I'm going to put 1 chlorine going up, 1 going down. We draw a dashed line to show things going back into the page. So chlorine going back here. I'm going to put another chlorine going back here. And then we'll have 1 coming out at us here and 1 coming out at us here. So 1, 2, 3, 4, 5, and 6 chlorines. So I've counted valence electrons, put my guy in the center. I'm going to fill everybody's octets. Every one of these chlorines right now has 2 electrons hanging out in this bond. So everybody needs 6 more. All right. I'm going to count. Well, there's 6 of these, and every one of them has 8. 6 times 8 is 48. So I've got 48 electrons represented, which tells how many I can have. So that's lovely. Now it's an ion. Remember the last thing we do with ions is we put brackets around it and say -1 for its charge. And that just lets our reader know, hey, an electron had to get added in order for everybody to have the number of electrons that they needed. So an expanded octet can also get that by adding pairs of electrons to the central atom. And we'll see that in class. The other new thing that we have here is dative or coordinate bonding. And this is with electron deficient species. An example of an deficient species is boron. And it's one of the most popular atoms that does this. So it only needs 6 electrons to be stable. However, it can still bond with others who have, let's just say lone pairs of electrons to achieve an octet. So if I were looking at boron trifluoride here, this is satisfied, right? Everybody has their number of electrons that they want. It's symmetrical, evenly distributed. It's nonpolar. It's really, really happy. But if something like ammonia came over, NH3, again, this is also happy by itself. But if it came over by my boron, or my boron trifluoride, my boron trifluoride would say, I wouldn't mind having a couple more electrons. And it would then make a bond here between my nitrogen and my boron, sharing this lone pair of electrons between the two of them. So we have a bond formed where they share the paired electrons, and we make a covalent bond. So that is our coordinate bonding. It's unusual, but it does happen, and mainly happening with boron trifluoride, especially you see it more, or boron trihydride, and then something else with that lone pair of electrons comes up, and then they make the bond there by sharing those electrons. We've talked a little bit about polar bonds and molecules already. We did that a couple of days ago. Remember, polar means to have that unequal distribution of electrons around the molecule that creates dipoles, and those dipoles don't cancel out due to symmetry. Remember that a dipole, or you don't know this yet, the dipole moment is shown by an arrow that points to a negative charge Or we can use these little squiggles here, the sigma, and we can say sigma positive for a partial positive side and little s partial negative side. So if I was looking at these two examples here, I can see that one, oxygen is much more electronegative than my carbons and also than hydrogens. So most of my electrons are going to hang out over here by my oxygens. So I'm going to say that this is my partial negative side, and this side over here is my partial positive side because we're going to have less electrons. So I can show that by drawing in my partial positive and negative, or what I can do is I can draw an arrow. Now, some people draw it directly over the top of it, and they put a plus on one end and the arrow pointing towards the negative end, or they do it just underneath. It's just personal preference. You'll find professors like one way or the other. Or they draw it underneath and they show and they say, hey, this pointy side here, this is the negative side, this is where most electrons are going. It shows the directionality of the electrons, which results in this side being the positive side. If I were to look at this molecule here, fluorine we know is the most electronegative atom of all of them. So these are going to have, each of these is going to have a partial negative end to it. Hydrogen's very unelectronegative, so it's going to be more partial positive. And again, in this, we could draw, more than likely this is pointing down. We could say that it's pointing down like so. So we can draw some directionality to these. This also helps by having these lined up. If there's another of this molecule next to it, it would probably be lined up in the same fashion because they're going to be slightly drawn to the other side, similar to how magnets work. And that's why that polar molecule is a little bit stronger than a nonpolar molecule, similar to why ionic is stronger than covalent. So nonpolar then is that equal distribution of charges across the entire molecule. If I was looking at something like hexane, which I've drawn here, hexane C6H14, well, carbons and hydrogens have relatively similar electronegativities. They're both pretty far to left, carbon here, hydrogen here. They don't really care about adding more electrons and gaining more. So they're relatively smaller. Now it's still slightly polar because carbon wants them more than hydrogen, but it's relatively nonpolar. We can see that here, they're just this distribution. And then same thing here, this molecule, carbon tetrachloride, is completely symmetrical. So even though my chlorines are way more electronegative than my carbons, because there's an equal pull all the way across the molecule, then we say that those all cancel each other out. So all the dipoles cancel, and we end up with a completely nonpolar molecule. So the important part about thinking about where our electrons are is we know that electrons repel each other. And that then leads to the shape that our molecules are going to make. And we refer to the shape that they make as a part of VSEPR, which is valence shell electron pair repulsion. In other words, non-bonding electrons or lone pairs are going to repel more than a bonding pair of electrons. That makes sense. They're sitting next to each other, whereas a bond is stacked. They have room to go out, shared between the two, whereas non-bondings are just stuck here and they don't want to get closer to each other. So we're going to look at shape. And we've looked at a lot of these shapes last year in chemistry. We've just got some new shapes to look at because now we have expanded octets and we've got some new structures. So we're going to look at the Lewis structure, right? And then we're going to look at the number of bonding and non-bonding pairs of electrons. And our shape is going to be drawn to minimize our repulsion, okay? Always trying to minimize repulsion. Okay, don't freak out. You got a chart to fill in. So I'm going to zoom this out. Take a second and pause the video and copy in what I have so far on this chart. Yes. And then we'll take a moment and then we'll go through and we'll draw the shapes based off of what we have here for bonded and lone pairs. So go ahead and pause. All right, so now that you have that copied down, you can see that this is grouped by bonded pairs. So that means the number of things that are attached to our central atom. So these are all central atoms with 2 things bonded to them. So 2 atoms bonded, 3, 4, 5, and 6. So that increases as I went down. And then our number of lone pairs is going to increase within each of our groups. So 0 through 3, 0 to 2, 0 to 2, 0, 1, and 0. Okay. As far as bond angles go, you don't have to know exactly the bond angle. However, what you do need to know is the relative angles of what's bigger and what's smaller. So you should know that a bond angle between a linear molecule is larger than the bond angle in a bent molecule, or that trigonal pyramidal is smaller than tetrahedral. So you want to know those relationships, where as opposed to knowing the exact numbers. They're not going to quiz you on the exact numbers, so which is nice. All right, let's draw some shapes. So they're going to start to ask you to draw shapes, they being AP College Board, to draw shapes that are in 3D. So we'll want to use some dashed lines, some solid, thicker lines to help show things that are going away from us, things that are coming towards us. Prior to this point, you didn't have to draw them in the correct shape. We're just excited that you could figure out what shape they're supposed to be, but now we want the shapes drawn correctly. So I'm going to draw my central atom as an X, my peripheral atoms as Ys, and then we'll draw on the rest. So if I have one central atom and 2 bonded atoms, okay, more than likely these are going to be double bonds, okay, and I can see that my shape here is linear, it goes straight across, and this is my bond angle here of 180 degrees. Something that's bent, now something that's bent means that my lone pair of electrons has come in to my central atom. I should zoom in more for you. So you can read it. So now a lone pair has come in. One of these bonds has gone away because now it's a lone pair. Remember, lone pairs take up more space. So that's going to push from it being linear. It's going to start to push down. And then if I add a second lone pair, it's going to push it even further. And I can see that in my bond angles. So here I'm going to have, say, a single bond to one side, double to the other, lone pair. So this angle here is my 120. And then my next one, I add in a second lone pair. It's going to come down. It's going to come down. It's a little bigger than 90. Lone pair, lone pair. But now this is down to 104.5 degrees, not Celsius, 104.5 degrees. Okay. So my lone pairs have pushed it closer. Now, if I add in a third lone pair, those are going to take up the 360 degrees around my central atom, which is going to force one bonded atom one way and the other way, and I'm going to get back to being linear. So I have my central atom, still 2 bonded atoms, but now I'm going to have, and this is 360 degrees, which is hard to draw on paper, but I'm going to have my lone pairs on top and on the bottom just coming all the way around, and now these coming out to the side. So I'm back to being linear again. Okay. Now if I have 3 bonded atoms, I'm going to have my central atom, and now I'm going to have them equally spread out because now there are no lone pairs, so they're going to take up equal amount of space. Remember, it's 360 degrees all the way around, right? 3-dimension. No lone pairs, so they spread out. A third of 360 is 120 degrees. Now, if I go ahead and I add in a lone pair of electrons, well, that lone pair of electrons is going to come in from the top, and it's going to push all of these bonds down because now it doesn't want to sit even with them. It's going to shove them down, just like how it did up here. It pushed those down. So I'm going to push my electrons, or my bonded electrons, down. So I'm going to have my lone pair hanging out at the top. And now I'm going to have one of these going back into the page, one of these coming forward at me, one coming off to the side, and they make that little pyramid of bonded atoms down and my lone pair hanging out on the top. Now, I'm no longer taking up 120 degrees. This is smaller. This is my 107.5 degree angle here between my bonds. Now, if I come in and add another pair of electrons, I'm going to get what's called a T shape. So we're going to push these guys together even more, where they're going to take up 90 degrees between each of them. So this guy is going to still have my central atom. And then I'm going to have my two pairs of electrons. And then now they're just going to come out. That's a Y, a Y, and a Y. And I make a letter T. Because now these are taking up all the space up here. These guys are shoved into one little corner to make a T shape. And this is my 90 degrees. Okay. Now this guy is an expanded octet, just like this one is, right? There's more than 8 electrons around our central atom. Now in my 4 bonded atoms, no lone pairs, that's a tetrahedral. We've seen that before. So in the middle, I have one coming up top. I have one going back, one coming forward, and one going off to the side. Okay. And those have a bond angle of 109.5. Now when I add in an electron here, again, that's going to push my bonds down. And it's going to push this guy that's up top. It's going to push him down a little bit to go back into the table a little bit. And I'm going to end up with a base that looks like a seesaw. And when we'll make these in class, and you'll see that it like rocks back and forth like a seesaw would. It's kind of cool. So we end up with this lone pair coming up top. And then we have our one that's going back, one that's coming forward over here. This guy comes forward here, and this guy comes back, and they make like 2 legs. I don't know. They're like this on one side and that on the other side. So they make like little legs to hold up the seesaw. And we say that that's complex, thankfully, and we don't have an angle there. Now, if I add in another pair of electrons, they're going to come up from the bottom. And that next pair of electrons, when it comes up from the bottom with the other one on top, is going to squish my bonded atoms to be flat. So I'm going to have these guys on the top and the bottom. And then these are just in the plane of the page, hanging out as a square. And they're flat, so they're in the plane of the page. So a square planar. So those are my 4s. With my 5s, okay, I'm going to have what's called trigonal bipyramidal. So I'm going to have my central atom, 5 things. So one's going to go up, one's going to come down, and the other 3 are going to space themselves out around the central atom this way. So one's going to come off to the side, one's going to go back at an angle, and the other one's going to come out at an angle. So this angle from this guy going down to this guy up to the side, this is 90 degrees. But then looking at these 3, they're spread out evenly going around it. So this is my 120 degree angle. Okay. Now, if I add in a lone pair, that's going to push one of these up. I'm going to end up with a square pyramid. So I'm going to have my central atom, my lone pairs hanging out, and then one's going to go back, one's going to come forward, the other one forward, the other one back, and then one's going to be up top. So I have this square comes up to a pyramid. And then finally, I have an octahedral, which is where I have 6 bonded atoms, no lone pairs. And that's similar to the, what's that, phosphorus hexachloride ion we drew before. We're going to have one coming up, one coming down, and then I'm going to have one off to the side, one to the other side, right? I'm replacing this one with a bonded atom, one here and one here. And it's called an octahedral because it has 8 faces. So if I were to connect all of these up and down, I'd have 8 different faces to my structure. All right, hang on because we got a little bit more to do. This might be a good time to like get up, move around, and get yourself a snack. Because now we're on to hybridization. All right. Hybridization is the overlapping of orbitals. Okay, so we've been talking about how electrons are shared back and forth, but really electrons are in orbitals and suborbitals. And those orbitals where the electrons are really overlapping one another and making what's called hybridized orbitals because they're overlapping, so now they're mixing together. Because really to say like just an electron being passed and forth, that's not super accurate. We can be more accurate, so we will be. So 2 types of bonds that we can have. We can have sigma bonds, this little sigma. This is the first bond that you can make with any other atom, is always a sigma bond. And a sigma bond is made from hybridized orbitals. That's where we have these overlapping orbitals. If I continue to make a bond between 2 atoms, that's when I get 2 single or double and triple bonds. And those are made from what's called a pi bond, little pi here. And this is the second or third bond made with any other atom. These are made from leftover p orbitals or a lone p orbital. And we'll take a look at these in a little bit. But the first thing we have to be able to do is identify sigma bonds and pi bonds on a molecular structure. So here I have this molecule. Yours just has C's and H's and N's. So go ahead and draw in your single, double, and triple bonds. Now the first bond made with any other atom is a sigma. So anytime we have an original bond, first bond, those are sigma. So sigma, I just realized my hand is in the way so you can't actually see that. So it's a sigma. This is a sigma. The first bond here is a sigma. This one, and the first bond here. So we're going to say the first bond is the top one, just to make us consistent. It really doesn't matter, but I'm going to do the top one being my sigma. Then the second or third bond made between 2 atoms is a pi bond. So this first one was a sigma. This next one is a pi. This first one is a sigma. This one is a pi. And that one is a pi bond. I'm going to pull up my finished notes so I don't miss anything for you. I have them on my phone from way back when. But my video I made was sideways, and that was super sad. Okay. So like I said, hybridization is a process in which atomic orbitals are mixed to form new identical orbitals. So this is where we're going to get into the behind the scenes part. And then at the end, I'm going to say, now this is how you can just identify it. So bear with me because it's important you know why, because AP likes to ask you to explain things. So if I have a molecule that only has single bonds, okay, so this guy only has single bonds. If I were to identify the type of bonds here, every one of these is a sigma bond because they're all just singular bonds. So I have 4 sigma bonds. Sigma bonds are hybridized orbitals. So I have 4 hybridized sigma bonds in this molecule, looking at carbon. Now, we know that bonds are formed using electrons, so I need to think about what electrons are present in carbon. Well, if I were to write its electron configuration in orbital notation for carbon, I would have 1s2, 2s2, and 2p1. Now, my 1s, these are your core electrons, and they do not bond. So I'm going to ignore those. My valence electrons are the ones that do the bonding. So that's these guys. These guys are the ones that are doing the bonding. Well, if I have 4 hybridized orbitals, that means that these 4 orbitals, this one, this one, this one, this one, are going to hybridize together to make 4 equal bonds. These 4 equal bonds came from an s orbital and 3 p orbitals. So we labeled it as sp3, and I can fill in my electrons. I had 4 valence electrons. So just like before, they fill in each their own spot before they would go and double up. So in this case, I would say that my carbon is sp3 hybridized. Okay. If I have a double bond, so in this case here, I've got a double bond. If I focus just on one carbon, I'm just going to look at my left carbon. First, I'm going to label the different bonds that I have. I've got a sigma. This top one is a sigma. The one underneath that is my pi bond. So I have 3 sigmas, 1 pi bond. My sigma, like I said before, is a hybridized orbital. My pi bond, we said my pi bond comes from a leftover p orbital or a lone p orbital. So this guy is a lone p orbital. I'm still looking at carbon. So carbon has my 1s2, 2s2, 2p2. Again, don't care about core electrons. They don't do any bonding. So I'm going to ignore that guy. I'm just going to look here. I have 1 lone p orbital. So that means one of my p orbitals does not hybridize. It stays by itself. So I'm running out of colors. This guy is going to stay by itself. And it's going to stay at a higher level. So I'm going to have my p orbital here. Okay. And then these 3 are my hybridized orbitals. These 3 are going to hybridize. This guy stays by itself. So I'm going to have 3 that come to equal energy level and mixed to make identical orbitals. And this came from an S, a P, and a P. So this is SPP or SP2 hybridized. Again, I fill in with my electrons, 1, 2, 3, and 4. So in this case, my carbon is sp2 hybridized because it has 3 orbitals that hybridized and 1 p orbital that didn't hybridize. And we'll look at what does that do to the structure further down. Okay. But what if I have a triple bond or 2 double bonds? They're going to work the same way. So again, label our bonds. I've got a sigma bond, a pi bond, and a pi bond. In this one, I've got a sigma, a pi, and a pi. So here in both of these, I have 2 sigma hybridized orbitals, and I have 2 pi lone p orbitals. So again, here are my electrons, and don't care about my core ones, so I ignore those. Now this time, 2 lone p orbitals. So these 2 are not going to hybridize. They're going to stay as p orbitals. These 2, it doesn't matter which lines technically, but these 2 are going to hybridize. So they're going to come together and they meet at some place in the middle. Okay, so a little higher energy than an S, a little less energy than a P, but they come together. And this came from an S, one of the S's and one of the P's. So this is SP. Then I fill in my electrons per usual. 1 here, 1 here, 1 here, and 1 here. So in either one of these carbons, they are both sp hybridized. Okay. Now, the fast way to count it is you just start counting bonds. So up here, we said this was sp3. So when I start counting bonds around my carbon, let's say I start here, I have S, P, 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 makes sp3. Here I have S, P, and this is one bond because there's only one hybridized orbital here. So spp, that makes sp2. Here, there's only one hybridized orbital here and one here. So sp makes sp hybridization. So you can just count the number of hybridized bonds or hybridized orbitals here, which is the first bond that I have. And by starting to count this, SPPP, that makes sp3. We'll never get into anything with a dehybridization. We'll just end, the highest we'll have is sp3. So what does this look like in a molecule? Now, it doesn't matter if electron domains are bonding or non-bonding. Remember, non-bonding are lone pairs. Each domain is going to require an orbital to hybridize. So if I see lone pairs of electrons, those are also going to factor into being a sigma bond because they're hybridized. So if I'm drawing this molecule here where I have sigma and pi bonds, this is the last thing, I promise. I'm going to have, and this is my nucleus, and really where my S is. And then these are my P's. So if my first bond is always a sigma bond, that's this guy. This guy's a sigma. This one's a pi. Sigma, pi, pi. What my pi bonds do, they're going to lock the conformation, which means that they lock my molecule into position. Okay, and I can see that here. So my first interaction I have is my hybridization. These two are going to hybridize together. They're going to overlap. They're going to come together and overlap. Okay, and when they do that, they overlap, but it's just this one bond. They come together and they overlap, and this guy can still twist and move back and forth. Now, as soon as I get a secondary interaction with these p orbitals, they just have a little interaction. They haven't hybridized, but they have attraction. So I went from having one where I could twist back and forth to suddenly adding in a second one. Now, these two are together. Now I can't twist anymore. I become rigid. If I add a third one, now I become even more rigid and I can't move as much. So it really locks it in. The second, maybe it can twist a tiny bit, but probably not really much at all. And then that third one definitely locks in my conformation. So if this guy came to be my third bond here, to be a triple bond, this would lock it in and I wouldn't be able to move at all. So that's how they can impact my molecule, right? These guys can all twist. This guy is stuck. This guy's definitely stuck, as are those two. Whew. That was a long bunch of notes, but good information. And even if this was like, Missy, I don't know what you're talking about, we'll practice this a whole bunch more. We'll label bonds in class tomorrow. Good work today.